Implicit differentiation is just a way to find the derivative or to find dy dx of an equation that we can't write as a single function of x. So something like x cubed plus y cubed minus 9xy equals 0. With any luck, you should know that this does not pass the vertical line test and is therefore not a function, which means that it cannot be explicitly written as y equals something all in terms of x. And anytime you have an equation that cannot be written as y equals something all in terms of x, so y as a function of x, then the way we will find dy dx for it, the way we'll find the derivative, is this method called implicit differentiation. And so these 4 things here are the basic steps for implicit differentiation, and we're going to talk about we're going to do them as we go through. Sometimes not all of those steps will apply. But just bear with me, as I'm not going to fully explain why everything happens as we do it yet. We'll see how we'll talk about it when we do the first problem. So our goal is to be able to differentiate both sides of our equation with respect to x. When we do that, we will end up getting some dy dx terms. And when we get those dy dx terms, we want to get them all to one side, factor them out, and then solve for dy dx. That's our goal. So we're going to have, a bunch of dy dx terms attached to things like x squareds or 3y's or something, and we'll factor out the dy dx and solve. Does that basically make sense?
Yes.
Yes, one yes. That's good enough for me. All right, let's do the first problem, and then whatever doesn't make sense will begin to make sense. So first off, we're given the equation y squared equals x. I'm going to real quickly here, maybe I'm going to real quickly here. I'm going to throw up this equation on Desmos, but you should know what y squared equals x looks like. What does that look like?
The square root of x?
That's half of what it looks like. Right. Y squared equals x is a parabola that's been turned on its side. Right? If we were to square root y squared equals x, we'd get y equals plus or minus root x. So we'd get a top half for positive root x and a bottom half for negative root x. Everybody see that?
Yep.
Okay. And so that's what I mean when I say it can't be written as a single function of x. Because if we write this out as y equals plus or minus root x, that's not a single function of x, right? That's 2 different functions that we're combining together to get this other equation, y squared equals x. Does that make sense? I hope. Okay. So our first step says take the derivative. And let's do this way. Let's take the derivative with respect to x of y squared and the derivative with respect to x of x. Now on the right-hand side, the derivative with respect to x of x, that should be pretty easy. What does that come out to be?
1.
1, right? But on the left-hand side, that's a little bit more of an issue because we're trying to take the derivative with respect to x of a term that has no x's in it. It's only got y's in it. You guys agree with that? That's a little bit of an issue, right? How do we do that? We haven't taken the derivative with respect to x of something that's not got an x in it, have we? Unless it was a constant. So how are we going to do that? Let's pretend that this is something like z equals y squared. And we want to find dz dx, which would be the derivative with respect to x of y squared, right? Would you agree that the derivative of z with respect to x would be the derivative with respect to x of y squared?
Yes.
Okay. So then how could we go about doing this to find dz dx? Any ideas? There's a rule that we have learned that should allow us to take this derivative.
The chain rule?
The chain rule is going to let us do this. Exactly. So shouldn't dz dx be the same as dz dy times dy dx? That's exactly what our chain rule says, right? That dz dx is dz dy times dy dx, or yeah, we've had different variables in there, but that's the same basic idea, right? dz dx is dz dy times dy dx. Good or no?
Yeah.
Okay, so what's dz dy? What's the derivative of y squared with respect to y?
2y.
2y. And what's dy dx? Well, it's just dy dx, right? So our derivative with respect to x of y squared is 2y dy dx. And anytime we take the derivative of a y term, but we do it with respect to x, we're using the chain rule, and we should end up with the derivative of this with respect to y times dy dx. So 2y dy dx equals 1. Does that make sense or no?
It does.
All right. So we end up with our derivative dy dx equals 1 over 2y. And that's our derivative. That's it. What's different about this derivative than any other derivative we found so far?
It uses y instead of x.
Yeah, it's got a y in it instead of an x. That's fine. There's no problem with that. Suppose we wanted to know what's the slope of the tangent line at the point, how about at the point 4, 2? That's a point that's on this, right? If x is 4, y is 2. What should the slope be? Should be 1 over 2 times 2. Should be 1/4. What if I asked about the point 4, -2? That point's also on this, right? But then the slope should be -1/4. And so this should be able to find the slopes of the tangent lines, or even the equations of the tangent lines. If we wanted to write this out, y minus 2 equals 1/4 times x minus 4, or y plus 2 equals -1/4 times x minus 4. So even though they have the same x value and different y values, this derivative will allow us to find the slopes of the tangent lines at both of those points. Y minus 2 equals 1/4 times x minus 4, right? And there's the tangent line up here at the point 4, 2. And the other one, y plus 2 equals -1/4 times x minus 4. And there's that one down here on the bottom. Everybody see that?
Yes.
Any issues with that?
No, that makes sense.
All right. Let's do another one. Let's find dy dx if y squared equals x minus 1 over x plus 1. So first off, as we take the derivative of the left-hand side of that, what should we get?
Two I.
Remember, we're taking the derivative of that left-hand side with respect to what variable?
X.
Right, with respect to x. So when we take the derivative of y squared with respect to x, we should get 2y times dy dx. Good?
Yes.
Okay. And what about the derivative of x minus 1 over x plus 1? That should be the quotient rule, yeah? X plus 1 times the derivative of x minus 1 minus x minus 1 times the derivative of x plus 1 and all over x plus 1 squared. And so we end up with dy dx equals, what's our numerator up here? X plus 1 times 1 is just x plus 1, and x minus 1 times 1 is just x minus 1. So the x minus the x will cancel, and the 1 minus the negative 1 becomes 2 in the numerator. And in the denominator, we'll have a 2y, and we'll have an x plus 1 squared. So we can simplify to 1 over y times x plus 1 squared. Good or no?
That makes sense.
All right. Just for fun, let's take a look and see what the graph of this looks like. We got y squared equals, was it x plus 1 over x minus 1 or the other way? X minus 1 over x plus 1. I think it was plus 1. No.
X minus 1 over x plus 1.
Yeah, that sounds right. And it looks like this. Good or no? Here's a nice point that's on it, the point 1, 0, yeah? X equals 1, y equals 0. What does it look like the tangent line is at that point? Looks like it should be a...
Vertical.
Looks like it should be a vertical line, right? So at x equals 1, y equals 0, we think that we should have a vertical tangent line. So let's see if that's true. All we have to do is plug that into our derivative. We have 1 over y, which is 0, times 1 plus 1 squared, which is 1 over 0, which is undefined, right? So it shows that we have a vertical tangent line at that point. Good or no?
Good.
Should our function ever have a horizontal tangent line? Just out of curiosity. What would make it have a horizontal tangent line?
The numerator would have to be 0, and so 1 would have to somehow be 0, and that would get kind of weird.
Right, 1 can never be 0. That numerator can never be 0, so there should never be a horizontal tangent line. And yeah, I mean, we might be approaching some asymptotes here that are horizontal asymptotes, but we don't have any horizontal tangent lines to our function. Right? And what about any other vertical tangent lines? We got one from y equaling 0 and x equaling 1, right? But also, what about if x equaled -1? Shouldn't that give us a vertical tangent line also?
Yeah.
It should, right? But if we look at the graph at x equals -1, it looks like it's approaching asymptotes, approaching a vertical asymptote, doesn't it?
Yeah, because that's an asymptote for the original equation too.
Right, exactly. If we were to go and try and plug x equals -1 back in here, we would find that our function is defined or undefined. There are no values on this equation where x equals -1. So we would say, no, there can't be a vertical tangent line there. Everybody kind of see how all that works? We got to be a little bit more deliberate with these values that we plug in when we've got some more complicated implicitly defined equations. Good, not good? Indifferent? All right, why don't you guys try to find the derivative dy dx of this one on your own? Take a minute or two to do that. How'd this go, taking the derivative with respect to x on both sides?
It made sense.
All right, on the left, we should have got 1, right? And what about on the right? The derivative of tangent y should become
Secant squared y.
times dy dx, right? Because we're taking the derivative of something that has a y in it, but we're doing it with respect to x. Everybody good with that? And dy dx should then equal what? Cosine squared y? Good or no?
That made sense.
Anybody have any issues with that? Any questions? All right, let's make this a little more complicated now. X squared y plus xy squared equals 6. And we want to find dy dx. So what are we going to do?
Maybe factor out the x's.
Okay, we could try to factor out an x. We could also factor out a y. We could factor out an xy if we wanted to. Sure, we could do that. Take out an xy, what are you left with? Just x plus y equals 6. Is that going to help us to take this derivative? You think that's going to make that derivative easier or no?
It could make it easier if you could use like the chain rule and the product rule together like we did last time. I don't know if it would actually make it easier, but it seems easier to me.
Okay, that's fine. Yeah, so we're going to have to use the product rule, right? Because we have a function x times y times another function x plus y. We could have just straight up used the product rule here for x squared y and xy squared, but factoring out the xy is fine. So let's try to take the derivative of this using the product rule. The product rule says, so here's our first function, xy, and our second function is x plus y. So the product rule says first function, xy, times the derivative of the second function, which is, what's the derivative of x plus y with respect to x? Should be 1 plus
dy dx.
dy dx, good. And then plus the second function, x plus y, times the derivative of the first function, which is xy. Now, xy itself is a product of two functions, isn't it? It's a product of x and y. And so we need to use the product rule on just xy also. So that'll be x times the derivative of y, which is dy dx, plus y times the derivative of x, which is just 1. And then that equals what on the right-hand side?
0.
0, because we got to remember to take the derivative of the right-hand side also. So this has kind of become a little bit of a mess. I think it would have been a little easier probably not to factor it first, but there's nothing wrong with trying to factor it first and seeing what happens. So let's do all the distributing we can possibly do and simplify this down as much as we can. xy times 1 is just xy. xy times dy dx is xy dy dx. And then over here we're going to have an x squared dy dx plus an xy. Then we're going to have an xy dy dx. And then we're going to have a plus y squared there at the end. Equals 0. Everybody good with that? And it doesn't sound like you can hear me.
We can hear you. And
Oh, you can. All right. I don't know. My AirPods died as I was in the middle of saying that, so I wasn't sure. Might have cut out, but everybody can hear me still?
Yeah.
yeah.
Okay, cool. All right. So now we just need to combine like terms and simplify. So we can bring this y squared to the other side. So we're going to have a negative y squared. And how about the xy and the other xy? That's 2 xy's, and we can bring those to the other side, so minus 2xy. And then on this side, we have an xy and an xy dy dx. So that'll be 2xy, and then we have a plus x squared. And all of those have a dy dx in them, so I can factor out the dy dx. Get dy dx equals negative y squared minus 2xy over 2xy plus x squared. Good or no? Any questions on that? You can still hear me, yeah?
Yeah, it makes sense.
Yes.
All right. All right, why don't you guys try this one out on your own? This should be a pretty easy one. And we've now got a point we want to evaluate our derivative at. So let's see if you can find the slope of, it shouldn't take more than a minute or two, but I'll give you just a second here to take a look at it. So give it a try. Pretty straightforward. Any issues with that? Are you guys finished?
Yeah.
All right, so you got 2x plus 2y dy dx, hopefully, equals 0. And simplify that down to dy dx equals negative 2x over 2y, or just negative x over y. And evaluated at the point 3, negative 4 to get, what, 3/4? And if we wanted to, we could have written in point slope y minus negative 4 or y plus 4 equals 3/4 times x minus 3. I didn't ask you to do that, but that would be the equation of the tangent line at that point. X squared plus y squared equals 25, right? And then y plus 4 equals 3/4 times x minus 3. And we can see that's our tangent to our circle at the point 3, negative 4. Good or no?
We're good.
Go back to that last page.
Yeah. Questions on it, or are you good? You just wanted to look at it.
Yeah, I just wanted to look at it. Thank you.
Okay. Yeah. All right. Let's take a look at this one. 2y equals x squared plus sine y. We want to show that the slope is defined for every point on this graph, which would mean if the slope is defined, that means that there are no vertical tangent lines to this function. And how will we do that? First, we need a
Derivative.
derivative. So derivative of the left, 2y gives us what? 2 dy dx. And on the right, it gives us 2x plus cosine y dy dx. Good or no?
It's good.
Okay. And if we subtract the cosine y, we end up with 2 minus cosine y on the left times dy dx equals 2x, or dy dx equals 2x over 2 minus cosine y. And so for the slope to be undefined, what would have to be true?
The denominator is never 0.
Right, the denominator would have to be 0 for it to be undefined, so let's take a look. 2 minus cosine y equals 0. When does that occur? If cosine y equals 2, well, the cosine of y is always what? Less than or equal to 1, greater than or equal to negative 1. So cosine y will never equal 2, and therefore the slope is defined for every point on this. And let's graph this just for fun. 2y was equal to x squared plus sine y. And we get this sort of like wavy-ish looking parabola, right? And even at these places where it's getting fairly steep over here, it never gets so steep that the tangent line would be having a slope that's undefined. Any questions on that? Any issues? Anything? All right, let's do some more. Everybody feeling reasonably okay about this so far? I hope. Why don't you take a minute and see if you can come up with the equation of the tangent line to this curve at the point 2 root 5 over 3 comma 2. So take 3 or 4 minutes and see if you can write that equation. How's that coming along? You guys still need a minute, or you guys got it?
Another minute.
All right, another minute, and we'll start talking about it. I'm going to put up the derivative right now just to make sure that everyone's got that right before they get too far. Or at least the first step of it. So hopefully you got that as your first step. And then would have rearranged that to be dy dx. Equals that. But we'll talk more about that in a minute. I'll give you guys another minute to finish up. Good now, everybody finish that one up. So if we're going to evaluate this at the point 2 root 5 over 3 comma 2, well, actually, that's way. Did everybody get that derivative? 18x over 18y minus 4y cubed? Or you might have had negative 18x over 4y cubed minus 18y. Both would be the same.
Mm-hmm.
All right, and so if we plug in 2 root 5 over 3 comma 2, the 2 root 5 over 3 goes in up here. So the 18 over 3 becomes 6, right? And then so we have 6 times 2 root 5, so that would be 12 root 5. And then in the denominator, we've got 36 minus, what is that, 32? So 4, or we get 3 root 5. So our tangent line should be y minus 2 equals 3 root 5 times x minus 2 root 5 over 3. Is that what you guys all ended up with?
Yes.
All right, let's take a look and make sure we've done this correctly, because you should always be able to graph these on Desmos and see if you did it right. So what do we have? We had y to the 4th equals, what was it, 9y squared minus 9x squared?
Yeah.
Okay, and then we ended up with y minus 2 equals, what was it, 3 root 5?
Yeah.
X minus 2 root 5 over 3.
Yeah.
And if we zoom in a bit there, we can see that our line there is tangent at this point, 1.491 comma 2, which is 2 root 5 over 3 comma 2. Good or no?
That's good.
All right. Okay. Next thing, and this is not something that will probably pop up on the AP test, but it's about a term that you've probably never heard of called orthogonality or orthogonality. If two curves are orthogonal at a point, it means that they share that point in common and that their tangent lines at that point are perpendicular. Okay, so that's what it means for something to be orthogonal. They have to share the point, and then the tangent line of each function at that point has to be perpendicular to each other. So given two different equations here, 2x squared plus 3y squared equals 5, and y squared equals x cubed, and we want to show that they are orthogonal to each other, that these curves are orthogonal at the points 1, 1, and 1, negative 1. So the only reason I bring this up, even though it won't show up on the AP test, is that there are a lot of times in Calc 3 and differential equations past this class and the class after this one, orthogonality comes up a fair amount. So you just want to be aware of that and what it is. So let's see if we can show that the tangent lines at 1, 1 and 1, negative 1 are perpendicular to each other. So we'll have to use implicit differentiation to take the derivative of 2x squared plus 3y squared equals 5, which will give us 4x plus 6y dy dx equals 0. And we'll take the derivative of this to get 2y dy dx equals 3x squared. Good or no?
Good.